All right, welcome back. This is part 2 of our discussion of point estimators. And while we spent the better part of this series talking about basic probability rules and distributions of statistics, this is our first attempt, well, second video, but still kind of that topic of our first attempt to try to correlate sample data into becoming predictors for population statistics. All right, because sample data I can always get a hold of. I can go take measurements or do surveys or whatever, but sometimes getting the population values, it becomes next to impossible. And so in the last video, we talked about the general basics of point estimation and walked you through some examples and kind of the concept of bias and those kind of things. And in our discussion, though, we never really came up with a strategy for how do you create these estimators. We just kind of took a wild guess at what we were using for estimators. So if you need to go back and kind of look at the definition of bias and kind of some of the strategies, I encourage you to pause this video and go back and watch that first one, and then come back to this one if you haven't already seen it. Things will make a lot more sense today if you've seen the other video. But nonetheless, as we start to move forward, that's kind of where we're going with this. In this video, we're going to spend more time talking about the basic, a couple of techniques that I can use to actually construct some estimators, and how we can kind of then, once I have the estimator, then we can go and apply the principles from that first video, checking if it's unbiased and, minimum variance principles and those kind of things. All right, so this video is more about the methodologies of how do we do it rather than what are we doing. Okay, and so that's kind of the difference. So without further ado, here we go. So we're into section 6.2. This is the methods for point estimation. We're going to focus mainly on two different methods for constructing this. They both function a little differently, and they both are effective for different forms. There are a lot of different methods and strategies. Even just basic curve fitting can get you a guess on an estimate a lot of times. But for us, I'm going to illustrate the method of moments, and then I'm going to illustrate the max likelihood estimation technique, or the MLE. All right, so the first one we're going to talk about is the method of moments. Okay, and so the requirements for that are that if the underlying distribution has m unknown parameters, okay, meaning that our PDF f is a variable of x and it has up to n parameters, and we're going to call those as theta 1 all the way up to theta m as being parameters of the population, that we can find moment estimators theta 1 hat all the way up to theta m by equating the first m sample moments to the first m population moments. So basically I go one parameter at a time, and I create an estimator for theta 1 that estimates the true theta 1 value or parameter, and then again I estimate theta m and use that to correlate back to theta m, and we can kind of start to build all of these. Now again, this theta notation, and we talked about this in the last video, this represents what we're using as our guess for the statistic. And theta, although we write it as theta generally, it's basically a statistic. This could be the population mean, the median, the max value. We covered all of those in that last video. So again, if you're confused, please go back and take a look at that. Okay, so the method of moments basically says that for the kth sample moment, I can create an estimator by doing 1 over n times the sum of I equals 1 to n of my xi raised to the k power. Okay, and so then the kth population moment, so if this is my sample moment value, the population moment value then becomes the expected value of x to the k. Okay, and that's kind of where we're looking at, and so that's where we're kind of working with this. Now, like I say, the mathematical formulation is, it looks like we said a whole lot of words, but we didn't really say a lot, but we really did. Okay, so I've got an example here that will kind of show what we have here. Okay, so our example then is that we're going to define a random variable x as being the time that a student works on an aptitude test. Okay, and so we define the PDF, and again, this comes from curve fitting or histograms or any other construction technique, that we can show that this is a PDF for the random variable x, which x is the time, and has one parameter theta on this, okay, such that we can define this PDF as being theta plus 1 times x to the theta power on the interval 0 less than x less than 1. Okay, and then it's 0 everywhere else. So that's our definition of our PDF. And this would be something, again, you establish from curve fitting, or if you're working homework problems, generally that's given to you as this. Again, we're not focused on how do we construct this but more how do we construct the estimator for the parameter that we're after, this theta parameter, if you will. Okay, and so what happens is that we have one parameter, theta, in this. Okay, so what we're going to solve for then is that the expected value of x is going to be equal to the sample mean for theta. So this is kind of what we're after. We're trying to get this to be my theta hat, okay, but I'm going to use that as my estimator onto theta. Okay, so to calculate the expected value of my function for random variable x on this, I'm going to integrate between 1 and 0. That was my limits that we had here, okay, of x times the probability of x and my theta parameter dx. So all I'm going to do is I'm going to plug in this formula into here, and we'll cover all of that. Now, obviously, what we have is the 0 elsewhere. Remember, the expected value, realistically, it's supposed to be an integral from infinity to minus infinity, but because of the 0 here, I've trimmed off and left only the 1 to 0 portion that is the non-zero value. So again, if you're struggling with some of these limits and where they're coming from, I encourage you to go back and look at our expected value video that occurred, a couple weeks ago on our video list. So all I'm doing is it's just a calculus problem at this point. So if I take my x, okay, then I get a integral from 1 to 0 of theta plus 1, x times theta plus 1. So what I've done is I pulled that x into my x that's here. That's where the theta plus 1 value comes from. Okay, and then I do my integral of this. And so this is just a straight power rule kind of thing. Okay, and so then this becomes then theta plus 1 over theta plus 2 is equal to then my sample mean, if you will, for that, because the expected value of x, when I pull that thing out, then is just the sample mean as we define it here. Okay, and so if we make the assumption then that theta is equal to theta hat, and so my estimator is equal to what I'm looking for in my population, this is the definition of unbiased. Okay, all right, so all we do then is, so now we have an equation based off of my theta, whoops, get back on here. We have an equation for theta plus 1 over theta plus 2 times x bar, or is equal to my x bar, my sample mean on this. I can rearrange all of this formula, and I can solve for, basically, we're saying, because what we're after is saying that theta is equal to theta hat, and if I rearrange all that and solve for theta out of that equation, I get the formula 2x bar minus 1 over 1 minus x bar. Okay, and that's known as the moment estimator for this particular problem. Okay, and so now I've got a construction technique that I take my sample data, that becomes my estimator, and then that will match my theta. You can see how we kind of worked our way backwards on this. Okay, so what we can do is we can compute any estimator theta hat using a sample mean x bar for this particular problem, the way that we kind of set all that up. All right, okay, but what we still need to do, and what we did in the last video, is that once I had my estimator, we still need to prove that he's unbiased. That's one requirement. And then we need to measure for the standard error, or the variance of this estimator, to basically prove that he's the best one, because we don't know that until I do this calculation. And for this particular example, I still don't know it because I didn't run that check, but this is how we can actually construct the estimator. So that's what this video is about, is how do I come up with these guesses, because out of thin air, you would not be able to generate this formula in most cases, unless you're just extremely gifted at doing this stuff, and I'm not to that point. So I have to kind of go through the math. So this is a technique for generating a formula that would work, and then you can test it according to the rules of the last video. All right, so that's the method of moments. Okay, the other method that we have is what we call maximum likelihood estimation, okay, or the MLE method. So for this one, what we have, and this one works pretty well for joint PDFs. Okay, and in this case, we have a joint PDF that has a PDF that has random variables x1 through xn, and then has some number of parameters theta 1 through theta m. Okay, and so this PDF is a function of these different parameters. Okay, this is known as a likelihood function. Now, how you come up with this, again, is kind of beyond the scope of what we're doing in this article, but if you've got the likelihood function, okay, we can now come in and kind of start doing some estimates. Okay, so the maximum likelihood estimates, or these MLEs, are those values of theta I that will maximize the likelihood function. Right, so we'll define our likelihood and then basically do some basic calculus to find the high points, the maximum value of those things. Okay, now the properties of this function are that for a large n, the MLE is approximately the same as that minimum variance unbiased estimator that we talked about in the last video. Okay, and that the MLE of any function, h is a parameter of my population statistics that we're trying to model, theta 1 through theta m, is the function h of theta 1 hat all the way through theta m hat of the MLEs. Okay, this is, sometimes you see this referred to as the invariance principle. Now, like I said, we don't do a lot with it, but it's kind of behind the scenes, right? That if I can get really good estimates on theta 1 hat through theta m hat, then I should be able to predict this. That would be a pretty good, a high likelihood estimator for what's going on with those parameters. Then all we have to deal with is the x's. All right, so again, to kind of illustrate what we're doing, let's try to apply this to a different problem. Okay, so we have an example. Okay, we're to define a PDF that is a random variable of, random variables x1 through xn, and then it has a parameter theta that we're looking to try to find in the population. It could be the maximum value, could be the number of occurrences, it doesn't really matter. Okay, and so by definition for this problem, we're going to say that this distribution, if you will, is defined by the formula theta plus 1 to the n power multiplied by the product operator I equals 1 to n of xi raised to some theta power. Okay, and again, that exists on the interval x being between 0 and 1. Okay, now if you look at this, okay, you've seen this before. Okay, we've talked about summation operators of AI is equal to A1 plus A2 plus all of this, and then the product operator of AI then is equal to A1 times A2 times all the way out to whatever my limit is. So that's the difference between these, and so that's this notation. But anytime you see this notation, the chances are, especially in probability and statistics, that we've assumed that all of my x's are independent. Okay, because if they're independent, that product rule, remember, if they're independent, when I go and try to do x1 intersect x2 intersect all the way out to intersect xn, the probability of that event, we said if they're independent, that we have a multi-rule that exists in which I can say that this is the probability of x1 times probability of x2 all the way out. Okay, and so that's the game, and a lot of times that's what's coming out of this this pi operator, this product operator, if you will. Okay, and so that's what that's representing. And so we can say that the f of x1 times f of x2 all the way out to f of xn is kind of what's happening. Okay, so when we do this, the likelihood function for this guy then, and they're going to write that as some script L usually, for my parameter theta then is going to be theta plus 1 to the n times the product operator of I equals 1 to n, xi to the theta. So that's what we had up here. Okay, and then we can kind of rearrange things a little bit, that's going to be then equal to then the theta plus 1 to the n times, again, that product operator. So what we want to do is we want to find the value of theta at which the likelihood function is maximum. So it's often easier to find the maximum of these product operators, though, because the problem that you have is to find a maximum function when a lot of stuff is being multiplied together. I can always undo this if I take the natural log. Okay, so anytime you see a product operator, a natural log is often a good solution. So if I take the natural log of this thing, of both sides of this, we're going to write this as an LL, as a script L. Basically, it means that this is the natural log likelihood function. Okay, it would then be the natural log of this thing. And when I do that, it uncouples all of these terms, all of these products. And so if I take the natural log of both sides, my natural log likelihood operator is going to be n times the natural log of theta plus 1, okay, plus a theta times the natural log of the products of all of these random variable x's, okay? And so I kind of spread things out, and we can kind of break all those parts apart. Okay, and so then to maximize this log function, all I'm doing is I'm taking the derivative with respect to theta of this guy. Okay, so all we've done really is that we've kind of broken pieces down. Okay, the natural log is good for getting rid of exponents. It's also good for breaking these pieces apart. So when I did that function, if you look on here, that the exponent n comes down, and I'm taking the natural log of that first term, plus then I take the natural log of, or I take my theta, if you will, times the natural log of all of the other stuff. It's kind of a product rule operator that's happening here. Now, again, I'm not too worried about that plus 1 that's hiding in here, all right, because for large values of theta, the plus 1 is reasonably insignificant on there. Okay, and so that's how we kind of start to work our way out of all of this. So once you get this natural log likelihood equation, I take the derivative, I set it equal to 0, right? And now I can solve for the value of theta as I start to kind of work this thing out, okay? And so then if we go in and we say that we still want theta equal to theta hat on this MLE method says that I can solve this for theta based off of all of this other data, okay? And so this then would be an operator that's based again on my sample data. I do have an n running around in here, okay? And then I can actually solve for that particular equation. So that becomes my estimator using this methodology. Now again, you still need to go back and check, is it unbiased? You need to check, is it the one with the minimum variance? Okay, but this is how you can construct a maximum likelihood estimation if you can establish these likelihood equations. So we had a likelihood equation here, okay, and then again, I took the natural log of that to do the log likelihood, which got me to this, and then all I do is I basically do a maximum calculus calculation down here. So that's all we did. That's all there is to it. So those are a couple of methods for us to be able to work with on finding point estimators. So a couple of techniques. Now again, it doesn't always work, and the challenge is still you've got to have some idea of this function, okay? And that's not really a trivial task, but for the examples in the book and the exercise that we're working with, if you've got this function, it becomes very easy to be able to back solve for my estimator, my theta hat, if you will, down here. Okay, so again, we'll save that for a discussion on another video or another series on how do you generate these functions in the first place. But if you have that function, this is a viable approach to being able to do it, and both become valid techniques. So we've talked about, this maximum likelihood. We talked about this method of moments. Those are just a couple of the more common techniques for being able to work with. But you notice that you've got to have these PDFs, and they've got to be in certain forms that line up with being able to do this. So this product operator, the likelihood is generally the better approach, whereas the other one, we had the max moments working with it. So anyway, I hope that's not been too confusing. I know it's kind of an abstract idea, but it's basically just a lot of calculus at this point to be able to solve for these. So like I say, as always, if you'll leave us some comments down below if something wasn't clear, or if you notice anything out of whack on this, please let us know and we'll fix it. Otherwise, if you like the video, that will help us out a bunch. And then, as always, be sure to subscribe to the channel. So with that, have a great afternoon. Happy engineering.